Calculus, we've had the opportunity to look at a couple different ideas in this unit. One is kind of your application of derivatives. We looked at some implicit differentiation as well as motion. Um, we also want to investigate some things regarding limits. And just kind of a reminder, if you had something like, say the limit as x approaches 3 of 4x minus 1, we saw that in that situation, you just plug the 3 in and get 12 minus 1, which is 11. And so in many situations, if you have a limit as x goes to a of f of x, it just ends up being f of a. Just go ahead and plug a into the function, and you can see what you get. But what we want to investigate today is when x is headed towards infinity or negative infinity. And it's kind of some review from before, but limit as x goes to infinity of x to the nth. Well, so if you think of a power function, for example, if we have a quadratic, or we have a cubic, or we have a quartic, or we have a quintic. If you notice in those situations, as x goes towards positive infinity, you can see that the y value, or f of x, also goes towards positive infinity. You can see that this trends upward, this trends upward, this trends upward, and this trends upward. So when you consider a limit as x goes to infinity of x to the nth, generally speaking, we're headed towards infinity. But suppose x is headed towards negative infinity. If you look back at this little graph that I drew, you can see as you head off to the left, in this case, you head towards positive infinity. In this case, negative infinity. Positive infinity, negative infinity. And the reason why is here, this is x squared, this is x cubed, x to the fourth, this is x to the fifth. So when you have an odd, it's headed towards negative infinity. Why? Because if you take some type of negative number and square it, you're going to end up with a positive. Whereas if you take some type of negative number and cube it, you end up with a negative. So that's something to keep in mind. As x heads towards negative infinity for x to the nth, it could be positive infinity if n is even. Negative infinity if n is odd. Now, suppose we put n in the denominator. Suppose we're looking at an example like the limit as x tends towards infinity of 1 over x to the third. If you would grab your calculator, I'm showing you multiple ways to kind of consider this a graphical approach using a table. But if I go into y equals and I just type in 1 divided by x raised to the third power, and you go ahead and check a table, and I plug in values that go towards infinity. So say I plug in 1, say I plug in 10, say I plug in 100. You can see that these values are getting significantly small. For example, 1e negative 12 means 1 times 10 to the negative 12 power. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's what that number is. And you can see that it's very close to 0. In fact, if you were to look at the graph, you can see that as x tends towards positive infinity by trace, as x goes towards positive infinity, the function value gets really close to 0. Same thing on the other side. as x tends towards negative infinity, the y value gets really close to 0 as well. So when you end up with this situation, 1 divided by a very large number cubed, it's going to tend towards 0. And it doesn't matter whether it's a positive number or a negative number. Either way, you tend towards 0. Now, sine of x, that's a different kind of situation. If you think about the graph of sine of x, you know the graph of sine of x looks like this. And at no point does this graph kind of tend towards one number. In fact, it just continues in both directions. It just continues to bounce back and forth between values of positive 1 and negative 1. And it never kind of hones in on just one value. So this limit, as x tends towards positive or negative infinity, it in fact does not exist. There are a couple special limits that we would also like to address. Normally in this class, we would have looked extensively at this limit right here, but we haven't had that time this year. But this actually tends to, if you look at the top, if you plug in the top, you get sine of 0 over 0, and the sine of 0 is 0. So the question is, what is 0 over 0? In this case, it's 1. And we'll show you why that is. Again, in this situation, we're not headed towards infinity. You can see that it's headed towards 0. Don't confuse that with headed towards infinity. In this situation, the limit is x tends towards infinity of sine of 1 over x. That'll be like, sine of 1 over a very large number. And you know that 1 over a very large number tends to 0. So sine of 0 is 0. So working with sine, some people say, well, if it involves sine or cosine, the limit just does not exist. Well, that's not the case at all, because I just showed you a couple of examples where that's not the case. So what we're going to do is we're going to use some laws of limits to confirm these ideas. And the best way to go about this is to factor out the largest term. So in order to argue this, so for example, you can say, well, I'm going to take 4 times infinity and subtract 1. Well, the idea of multiplying by this infinity here, that's really confusing to think about. In fact, it doesn't really help us much. And if you think about, well, 4 times a really big number minus 1 is still going to be a really big number, and that is a good way to think about it. But we're gonna use a little bit different operation to confirm this. We're gonna factor out x. So I'm gonna write as limit as x goes to infinity of x times 4 minus 1 over x. Okay, and we'll use that to justify this limit. I'm going to use n for a very big number, and I'm going to use 1 over n for a very small number. It's going to be very close to 0, okay? So if I am headed towards infinity, I'm going to plug in a very large number. So very large number times 4 minus 1 over a very large number. Notice 1 over a very large number is going to go to 0. So it's going to be like 4 times n. And 4 times n, 4 times a very large number, it's going to be another very large number. So this limit does go towards infinity. Now, watch how this can be different for your second example. Again, if you were to just say, like, plug in a large number squared minus 3 times a large number. Well, that would be like infinity minus infinity, which must be 0. This type of thought does not work very well, because the first term is getting larger much more quickly than the second term. The best way to show this is to factor out x squared. Limit as x goes towards infinity of x squared times 1 minus 3 over x. As you plug in a large number and square it, 1 minus 3 over a large number. And 3 over a large number is 0, so you get n squared, which would be infinity. For the next one, now we're headed towards negative infinity. So I have the limit as x tends towards negative infinity of, I factor out the x squared, I'm left with 1 minus 10 over x. Plug in a very large negative number squared, times 1 minus 10 over a very large negative number. This is going towards 0, because 10 over a large number is going towards 0. And if you square a negative number, you do get a positive. So we'll head towards positive infinity. you consider the next example, I'm going to factor the largest term out of the top and the largest term out of the bottom. So I get the limit as x tends towards infinity of x times 2 over x times 1 minus 1 over x. Notice that the x's cancel, and you get 2 over 1 minus 1 over x. If you plug in a large number, will go towards 0. So you get 2. That limit is 2. Now, just to confirm the idea, I'm going to go to my graphing calculator. I'm going to type in 2x divided by parentheses x minus 1. And when we check out that graph, you can see as I press trace, as I move to the right, look at what's happening. As the x values get larger, what's happening to the y values? You can see that the asymptote is at 2. So you can see the y value is staying very close to 2. If you check out the table, if you increase your x values dramatically, you can see how the y values are staying very close to 2. So this does confirm that idea. In the next one, limit as x goes towards negative infinity of x cubed times 4 minus 1 over x cubed. In the denominator, I factor out an x squared. And you have 1 plus 2 over x minus 3 over x squared. Hopefully you're used to it by now that if you see any term in the denominator like that, if you're headed towards infinity, they will in fact go towards 0. So those are all gone. And the x cubed over x squared will just reduce to x. Notice you get 4x over 1. Now remember to plug in a very large negative number. And if you plug in a very large negative number, the result will be negative infinity. The next one, there's nothing to factor out of the top. But if I do factor out an x squared on the bottom, we get 1 minus 3 over x plus 7 over x squared. Again, per our work earlier, remember those go towards 0. As you plug this in, 6 over a very large negative number squared, we do get 6 over a very large negative number, which is going to take you towards 0. A few more examples. If you notice in this situation, I'm going to try to show you something interesting. Notice how the top and the bottom were even in terms of your exponents, even meaning the top was 1 and the bottom was 1. The answer came out to be 2. Notice in the next situation that the top won out, so it was x cubed over x squared. So your answer is going to either be positive or negative infinity. In this one, the bottom had a greater degree, so the bottom wins out. It's going to go to 0. So I can look at this ahead of time. I can see that the bottom is greater in degree. So I can anticipate that the bottom will win out and I'll make it go towards 0. Let's show that that's the case. Notice how this is gone. X over x squared, that's gone. That reduces just x. So we get 3 over a very large number, which is going to be 0. The next one, if you consider a cubic as x tends towards infinity, I think the result should be infinity. Let's confirm that algebraically. As I factor that, notice that the 2 over the x squared is gone. So I have 8 times a very large negative number cubed, which is going to go towards infinity. If you look at the next one, I see that the numerator is of higher degree. So the numerator should win out. It should go towards positive or negative infinity. So I factor out the x squared out of the top and the x out of the bottom. You can see what I have. Again, the terms with x squared and x in the denominator will go away. And one of the x's will cancel. And so we will get a negative 6x on top and a 1 in the bottom. Now plug in a very large negative number. Negative 6 times a very large negative number. And a negative times a negative will be a positive, so this should go towards positive infinity. 5 more minutes. All right, a couple more. Here I'm going to factor out an x squared limit as x goes towards negative infinity. So you factor out the x squared, we get 5 over x squared minus 2 over x minus 3. Notice that these go to 0. They're gone. So you get negative 3 times a very large negative number squared. So that would be negative 3 times a large number squared, which will result in a negative infinity. As x goes towards infinity, you're going to factor out an x out of the top. You're left with 4 minus 1 over x. And the bottom, factor out an x. And you are left with 5 over x minus 6. Notice how these two are gone. Those two go away. And so you get 4 over negative 6, which is negative 2/3. And if you want to confirm your result, go ahead and graph that. I promise you'll get it. Again, even when you have very large numbers, this is a 1 billion here on the top, 1 billion on the bottom. They really don't impact it in the long run because infinity is so much larger than those numbers. If you look, the denominator is larger, you know that this is going towards 0. And I didn't show that algebraically. You sure could, and you should. But just for sake of time, I'm not going to do that. Let's look at a couple of a little bit more difficult. Got some square roots here. Limit as x goes towards infinity. On the root of, I'm going to factor out an x squared. We get 5 plus 2 over x squared. And the bottom, factor out an x, and you're left with 7 plus 1 over x. Now, as you're headed towards infinity, notice that those will go away. Okay? And you can take this x squared and move it out front by making it an x. And then those will cancel as well. So you end up with the square root of 5 over 7. In the next situation, similar. Limit as x goes towards infinity. 8x squared over square root of, if you factor out x to the 4th, you get 2 minus 6 over x to the 4th. Notice the 6 over x to the 4th goes away. You put that x to the 4th out front by making it x squared. And when you do that, notice that the x squareds cancel. And we get 8 over the root of 2. Multiply top and bottom by the root of 2, and we get 8 roots of 2 over 2, or 4 roots of 2. Limit as x goes to infinity, we're going to factor out an x to the 6th, 2 roots of x to the 6th times 1 over x to the 4th plus 1 minus 3x cubed. Notice you can put that x to the 6th out front. So limit as x goes to infinity, as I move the x to 6 out, becomes x cubed times the root of 1 over x to the 4th plus 1 minus 3x cubed. So let this go to 0, it's gone. And so you get 2x cubed minus 3x cubed. that'll be negative x cubed. And as you look at x goes to infinity of negative x cubed, that's going to be a negative infinity. A couple more problems. Sometimes you can't confirm algebraically. You need to think about the graph. For example, negative 3 sine of x. You know that this has an amplitude of 3. Goes up to positive 3, goes down to negative 3. As you head towards negative infinity, so as you go this way, you can see, again, the graph bounces back and forth between 3 and negative 3. It never isolates down to one value. So, in fact, this does not exist. The same thing would be for cosine. I don't really care about the 5x, just means it repeats itself more often. But it bounces back and forth between 1 and negative 1. You can see that this does not exist. But soon you're going to say, well, every time it involves sine, the limit does not exist. And that's not the case at all. In this situation here, we can factor out an x. As you factor out x, you get sine of x plus 1. Now, I want you to think about this. We try to reconcile what this will be. The biggest value that sine can be is, well, not plus 1, but plus 3. The biggest value that sine can be is positive 1. The smallest it can be is negative 1. So at best, you're going to get 1 plus 3, which is 4, so you get 4x. At worst, you would get negative 1 plus 3, which is 2. You get 2x. Well, whether you get 4x or 2x or something in between there, if you plug in a very large number, you're going to get infinity as a result. So the answer is infinity. Finally, the last example. Find the horizontal asymptotes for the following. In order to find the horizontal asymptotes, we have the limit as x goes towards positive infinity and the limit as x goes towards negative infinity. I'm going to go ahead and factor out an x. And when you do, you get 4 over x minus 1 divided by x times 3 plus 2 over x. Notice that these go to 0. Okay? And these cancel. So you want to say negative 1/3. But I just want you to think about this for a second here, okay? Think about plugging in a very large positive value here. 4 minus a very large positive value over 3 times a very large positive value plus 2. Hopefully everybody can see that you're going to get a negative on top and a positive on bottom. And a negative divided by a positive is going to be a negative. If you were to switch that around, you would say that 4 minus a very large negative number divided by 3 times a very large negative number plus 2, you would get a positive on top and you would get a negative on bottom. Either way, the result is negative 1/3. So the horizontal asymptote, either way, is y equals negative 1/3. We're going to use that thinking to try to work through this last one, because it is slightly different. I'm going to factor out that x squared. I get 2 plus 1 over x squared. And then I'm going to factor x out the bottom, and I get 3 minus 5 over x. And draw the x squared out, so I have an x roots of 2 plus 1 over x squared, all over x times 3 plus 5 over x. Notice as the limit goes to positive or negative infinity, these will disappear. And the x's go away. And so you leave your answer as root of 2 over 3. But be very careful. Because if you consider this example, let's let x tend towards positive infinity. If you go towards positive infinity, hopefully you can see that if you plug in a very large positive number, you're going to get a positive on top divided by a positive on bottom, which will result in that positive. So yes, y equals the root of 2 over 3 is one of your horizontal asymptotes. However, if you tend towards negative infinity, watch what happens. 2 times a very large negative number squared plus 1 divided by 3 times a very large negative number minus 5. Hopefully you can see you get a positive on the top, but in the bottom, you end up with a negative. And so, therefore, it's y equals root of 2 over 3 is one of your horizontal asymptotes. Y equals negative root of 2 over 3 is one of your other horizontal asymptotes. If you don't believe me, check out your graphing calculator so you can see. It's always good to just plug in those values to see what's happening. Anytime you get the square root, funky things happen with the positive and negative. I have 2x squared plus 1. And I'm going to divide that by 3x minus 5. As you check out your graph, there you have it. As you trace, as you head towards positive infinity, look at what happens. The y value stays positive. In fact, about 0.6 is about square root of 2 over 3. So you can see it's positive that direction. But if you head towards negative infinity or back the other direction, watch what happens there. Notice how it stays below the x-axis. Negative 0.26, 7, so on and so forth. If we check the table, you can see what's happening here. 0.47. If you head towards negative, let's say 10,000, you get the negative value. So positive one way, negative the other. Good job. Long video, important topic. Good luck. We'll see you in class soon.